Hello, in this recording I'll record the modern view of the electron. Now here is a PhET simulation of a light source, which is shown as a blue ray gun, and it's hitting a box full of hydrogen, and a small area of hydrogen is exposed. Now initially I've selected monochromatic light to go into this box, and you can see the light as it's flying through the actual individual photons. These are wave packets indicated by the colour of the light. And I'm going to go around and select a magic number, which is 620 nanometers, which corresponds to 2 eV. 1240 is 1 eV. And so you get used to this sort of orangey light. As in our experimental setup, this is the actual real-life experiment. You can see in the top left-hand corner we've got a switch to a real experiment. We get the hydrogen lines out. There's some hydrogen in the box. Now, if we go to predictions, I've automatically set it to the most recent research, which is quantum mechanics. The electrons indicated as a wave, and you can actually see the individual electrons. In the center is a little red dot, which is the mark the hydrogen nucleus is, which is a single proton, and the actual individual electrons are different different waves. So I'm going to build up there. Initially, it started off with us not realizing what atoms were. There was a Greek prediction that they were small spherical balls, and in 1905, Einstein discovered that for the first time atom means atom, cannot be cut. Here we have a plum pudding, or just a blob with an electron inside it, and the electron shakes and oscillates like a little mobile phone antenna. And you will see that in this early model, this is before they discovered the nucleus, the sun electron, you have this only re-radiate in the ultraviolet, or dominantly radiate back in the ultraviolet. For that car to go past, there's a quiet suburban street. And so that was the JJ Thomson's model, and they discovered the nucleus. And of course, as soon as they discovered the nucleus, they've got a very small dense charge, a very small electron. They thought JJ Thomson thought the electron was small, and that initially caused a major problem because the electron would go in and collapse the nucleus and explode. So Bohr came up with the idea that, still hanging on to the idea that because the electron is so small, it must be so light, it must be very small. The electron must go along these fixed tracks, and therefore in fixed tracks cannot disappear. And you can see the electron is a little blue dot going in a circle, and these are called orbitals. But on the other side, you have, for the first time, energy levels. One of the misconceptions is that the energy is quantized. The actual angular momentum, or the actual track, is quantized, and that leads to a unique energy level. You see it off on to the right hand side. So we've got Bohr atom. And rather curious, this was established in 1916, and this is where the HSC syllabus is up to. You have de Broglie, which we also study in quantity quark, and he, around 1924, came up with a electron as some sort of wave in the track, some sort of midpoint between the classical physics. It also had glass. Now we come to the Schrodinger wave equation, and the electron as a beautiful big wave. And in this, the electrons are the size of atoms, and this is the modern theory. And beautifully off to the side, we have the energy levels. Now, not only do you have different energy levels for different orbitals, but you've got different angular momentums, which are all quantized. And you can see the light going out up here. As you get light of different wavelengths or different energies going in between energy levels, they get different colours coming in. You can see the p orbital there. You can see the wave of electrons, and this is the when the wave of electrons in a metal, and that wave hits the lattice frequency, it gets very energetically efficient or inefficient, creating a band gap. Now, previously, this is very good, but this is just a PhET simulation, a great simulation. But if you go into the internet and type PhET dipole moment, you can go to this site and see a full quantum mechanical picture of an electron moving. Here we start off with a P1s bottom to a 2p orbital, and this is the actual shape of electrons. They're very large, soft, fluffy things, thanks to Schrodinger wave equation, which says that the tightness of the wave function is proportional to the mass. So you get a very loose, soft wave function, a very loose, large wave function if you get a very small mass. It's one of those surprising things, counterintuitive, that normally if you want to get a smaller thing, you chop it off and it's lighter and smaller. But in quantum mechanics, if it is lighter or less massive, it's actually larger in size. And all the electrons actually slide through each other in space. And here I've selected another orbital, a different shape, and different colours refer to the actual phase of the electrons. This is probably more akin to the electrons spinning and moving. This is a particularly beautiful orbital to look at. You can see it's got high angular momentum, but you can see the arrow spinning around at high speed in the bottom right hand. And I'm rotating this to have a look at it. This is yet another orbital. This works on this orbital. On the top of the screen you can see a red line as the electron goes between energy levels. The energy is not actually quantized, it's the angular momentum which is quantized. The energy is the energy level. This is a beautiful electron, and you can see the waves in the electrons, and when those waves hit the wavelength of the lattice, you get a band gap happening. This is, you see it oscillating. What's happening is an electric field is coming in from a photon, and it's gently caressing the atom and pushing it up to different quantum levels. It's by Falstad, one of the truly great programmers of our time, and I recommend reading through all his work. This is another electron being excited by a photon being pushed up. So you've got a electric field, oscillating electric field, and it interacts with the electron. The very centre where I've got the cursor sitting there, just around there, much smaller than 1 pixel on the screen, is the nucleus. It's got a very large mass. Here we go back again to the final quantum mechanical model, and we can start to see some of the pictures that we're seeing here. That animation 4 is what happens when the light particle actually hits it. What I'm showing here is that in quantum mechanics, if you don't have light of the correct frequency coming in, it does nothing to the atom. It needs sufficient energy to knock things up. Very similar to the photoelectric effect, you need electrons of sufficient energy. Here I've just hit resonant frequency around, I think it's 95 nanometers.